All right. Hello, Namaste, and welcome everyone. Welcome to this problem solving session. Today, we will be solving problems related to basically lecture 9 of this course. And yeah, I mean, so maybe I will give a brief, like, summary of what was covered in this week's material, and then we will start solving problems, and we will solve few problems, and yeah, we'll see how it goes. Uh, so maybe let me just start sharing my screen. Uh, So the screen is shared, I suppose, and right. Okay. Create a new notebook. This is section 9. Okay. Hmm. Hmm. Okay, so let's get started. I will try to finish this lecture a bit earlier. Uh, so so this is lecture 9. So lecture 9 basically was all about what? It's it's all about what? It's about estimation theory, right? So lecture 9, I mean the ninth week was basically about estimation theory, where you study basically types of estimators, yeah, and then briefly some properties of estimators, right? So like these are the two broad topics. What do you study in types of estimators? I think broadly you have studied two of them, right? Moment estimators and MLE estimate, maximum likelihood estimate, right? And the in properties you basically study again two things: biasness, and the second property that you study about is basically consistency. So so what should I do? Maybe I'll just solve problems, right? And or what should we do? Maybe I'll just give you a like definition, like Wikipedia kind of definition of these things, and then we can proceed, right? So the first thing is what is moment estimator? What are these things? So moment estimators are, so let's say you have some parameters theta, which is a tuple of theta 1 to let's say theta k. So these are like the parameters of your distribution, right? And so you have a random variable w, which is coming from some distribution fw of w parameterized by theta, right? So to estimate these parameters theta 1 to theta k, what you do is you first calculate the first k moments of this random variable w, right? So let's say you define mu1 to be expected value of w, so the first moment, right? And that comes out to be what g1 of theta 1 to theta k, right? So g1 is some function, okay, some function of theta 1 to theta k. Similarly, you find mu2, which is expected value of w square, which is equal to g2 of theta 1 to theta k. and so until mu k. Expected value of wk is equal to gk of theta 1 to theta k. So you first find out these things, right? Then, so these are like you just calculate them by, uh, through analytical techniques, right? I mean, just solve for these expectations, these moments, and you will find what G1, G2, GK are, right? Then what you do is, then you assume that you have some samples, small W1 to WK, which are sampled from this FW, right? Theta, and these are, let's say, ID. So uh, so basically you have samples from this distribution. Now using these samples, you need to estimate mu1, mu2, sorry, theta 1, theta 2 till theta k. So what you do is you basically find empirical estimates of this mu1 till mu k, right? So what I'm trying to say is you first find mu j hat, which is equal to 1 by n summation I equal to 1 to n w I raised to g, right? So basically you will have a set of mu1 hat, mu2 hat, right, till so until mu k hats, right? So these are these. So here you have like the exact expressions. Now here you have some empirical estimate of these things, right? So basically in the next step you club these two things, right? I hope you are getting my point. So what I'm trying to say is you have mu1 here, you have mu1 hat here, you have mu2 here, you have mu2 hat here. Since you don't know exactly what I mean mu1 is, because theta i's are unknown here, you take a estimate of mu1, which is mu1 hat, which is a like using your law of large numbers, right? And after you have calculated this, you just substitute club these two things. So what you do is you basically come up with a set of k equations. So you just say that okay, mu1 hat is equal to g1 of theta 1 hat till theta k hat. Mu2 hat is g2 of theta 1 hat till theta k hat, and so on till mu k hat, which is equal to gk of theta 1 hat to theta k, right? So, uh, so you solve these. So solve these set of equations. So set of equations to uh, for theta 1 hat till theta k. Let's call it theta. So this is the basically the overall idea, right? So, I mean, what we are doing is nothing high-fi. You first need to find what these functions are, G2, G2 till Gk. That can be easily obtained using your analytical simplifications. And then you find empirical estimates for mu1, mu2 till mu k using sample means, right? Law of large numbers. And once you are done with that, you just club these two, okay? Substitute mu1 hat for mu1, right? And like mu2 hat for mu2, right, and so on till mu k hat. And then you simply solve for these variables theta 1 hat to theta k hat, because g1, g2, gk are known, mu1, mu2, mu2, mu1 hat, mu2 hat till mu k hat are known using these things. You solve for theta 1 hat to theta k hat, and these estimates are eventually what you call as your MLE estimate, sorry, moment estimator, moment estimator. So these are the moment estimators. What is the next thing? The next thing is basically your okay, okay. The next thing is basically your maximum likelihood estimator. Esti- So what are or MLE for in short. So again, something which is very commonly used in a lot of applications, especially nowadays machine learning and with MLAI models are basically based on MLE estimators. So they heavily rely on these things. So yeah, again, an important topic. So again, so the setup is the same, right? Uh, Setup is the same. I'll just copy this, paste it here. Okay. Uh, Now what you do is, so you have these unknown parameters and you have this parametric distribution. Okay. Now what you say is, basically you have these W1 till WK that are sampled that you have that is given to you IID from FW of W theta. Okay. Uh, so what you do is you first define something called likelihood function, basically L of this is W1 till WK given theta. Okay, and this is nothing but product of FW of WI theta. Okay, I going from 1 to K. Okay, so you first define this likelihood, then take log of this. So let me call it L of theta, which is nothing but log of L of W1 till WK theta, which is nothing but sum of ln f W Wi theta I equal to 1 to K. Okay, then the estimate, the final estimate. Okay, so theta MLE that is obtained by doing an optimization over R max. Okay, R max over theta of L of theta. Okay, so basically R max over theta of summation of I equal to 1 to K ln log f W of Wi theta. Right, so it's like finding the value of theta which maximizes the probability or the likelihood of these samples. That's all. So so you can think of adjusting your parameters theta such that these observations are most likely to be seen, right? That is why it's called the maximum likelihood estimators. Okay. There are deeper understanding of MLE from the point of view of KL divergence and all those things, but we won't go into those things here. Okay. Uh, so you, so it's just a simple optimization problem for you. Okay. Nothing fancy, simple thing. Uh, I think what. So maybe I'll just discuss the properties of estimators. So let's say you have a estimator which is T. Okay. I mean, let's say T is an estimator for theta. Okay. So theta is a parameter, right? And theta is a parameter, and T is an estimator of theta, which you can either represent by theta hat or T. Maybe I will write T of W1 to N. So you have where W1 till N are sampled IID from FW of W theta, right? So this is your parametric distribution. These are your samples, and T is your estimator. Okay. So okay. So T is basically a function of these random variables, right? So these are random variables. T, this thing is a function of random variables. Okay. So this means that this T itself is also a random variable. Okay. and hence you can talk about the property of this new random variable, that is t. Okay, so there are two properties of interest to us. Okay, first property is that biasness. Biasness, what does it mean? So if expected value of theta hat is equal to theta, then t is said to be unbiased, right? So it's like, so biasness basically means that, on an average, this estimator will give you the exact value of this parameter theta that you're looking for. Okay, so that is why this expectation is there, right? And the second thing is consistency, right? What do you mean by consistency? So if they so if limit n going to infinity of variance of theta hat. So theta hat, remember, is a random variable, right? So since it is a function of random variables, it is also a random variable. Limit n tending to infinity of variance of theta hat. If this thing is equal to zero, then t is said to be consistent, right? So these are the two properties, unbiasedness and consistency. So why is it called consistent? So you can think about, so it's like saying that, asymptotically in the limiting case, when you have a lot of samples, uh, this this estimator will have zero variance. Okay, meaning that it will give you exactly the value of the parameter that you are looking for, right? Well, not exactly. I mean, it might not. So it might not give the exact value. It will give you some value, but it will be very consistent for that value, right? I mean, okay, let me repeat myself. What I'm trying to say is, if you have infinite number of samples from this distribution, then this estimator will keep giving you the same value again and again without any variance, or right, because the variance is zero. Uh, so I mean, this is another desired property basically, right? I mean, you don't want your estimator to, vary a lot if you have enough number of samples. However, consistency alone is not of like significant use, because it can keep giving you the same value of the parameter theta. However, that value might be, wrong basically, right? It might be an incorrect estimate of the parameter theta. Similarly, an unbiased estimator is in itself not a good thing, right? I mean, you can have an unbiased estimator. However, if the variance of the estimator is very large, it will mean that you will have to repeat the experiment a lot of time to, exactly find out the value of your parameter with high confidence. So what is desired is the that your estimator should be unbiased and consistent at the same time. Okay. So uh, yeah, I mean, just keep these things in mind. Okay. Uh, okay. So I think we can get started with some problems. Okay, and we will see how much we can do, because I have to leave early today, so I'm not very sure about how much time we can spend today. Okay. Nonetheless, I will try to solve few basic problems that will be helpful to you. Okay. Uh, all right. So the second. Okay. Yeah. So here is the first question. Let's start solving. Okay. So here is the first question. Uh, so Uh, so here is the first question, right? So x1 till xn, these are IID random variables, okay? That is sampled and given to you. Uh, it is given to us that expected value of xi is equal to mu and expected value of xi square. So the two moments is less than infinity for all I. Equal to. So for all I, these two conditions are satisfied. So it has a mean first moment of mu and the second moment is bounded. That. So it's not bounded, it's finite. That is what we know. Okay. Now we are given this estimated t of x, okay, which is t of x1 till xn. And what is this estimator? This estimator is 2 over n into n plus 1 of summation I equal to 1 to m I xi. Okay. For this is for parameter mu. So this is what it is. So the question that is asked is T of x biased question mark or is it consistent or not? So these are the two questions, right? So I hope you get the problem. It's pretty straightforward. You have been given samples x1 to xn. The first moment is mu, that is a parameter you want to estimate, right? And expected value of xi square is less than infinity, that is given to you. The question is, let's say this is your estimated t, which is given by this expression. Okay. The question is this estimator biased or not, and is this estimator consistent or not? So these are the questions. Just give me a second. Okay. Yeah. Sorry for the this thing. Uh, Anyway, so I hope the question was clear, right? I will just solve it. So let's go about solving it, right? So so t, let's say I am defining t to be 2 over n into n plus 1 summation over I times xi I equal to 1 to n. Okay, this is given. Uh, what we need to do is for biasness we need to find what expected value of t, right? And for this we have to find the variance of t. That's all. So let's see what it is. So expected value of t will be what? So this is a constant. 2 over n into n plus 1 will come out. Summation over. So by using linearity of expectation, I times expected value of xi, right? So this is what this thing will be. And this thing, let's say, I mean, this is mu. Okay, so this is given to us to be mu. So mu will come out because this is constant for all I. So this will be 2 mu over n into n plus 1 summation over I equal to 1 to n. This will, so okay, again, this thing is equal to, I don't know if you remember this, but this is equal to n into n plus, n into n plus 1 by 2. This is what it is. Okay. So substituting it, this will be 2 mu over n into n plus 1 times n into n plus 1 by 2. This thing cancels out and this is equal to mu. So expected value of t is equal to mu. This means that it is unbiased, right? Because I mean t was an estimator of mu, and we can see that the expected value matches. So it is unbiased. Okay. Now let us look at the variance of t. What is the variance of t? So again, by using the properties of variance, right? What will this thing be? So this is a constant 2 over n into n plus 1, 2 over n into n plus 1, that it will just remain outside. And these are IIDs, so just uh, I mean we don't need to look at the cross terms. So this will become I equal to 1 to n, and variance of IXI. So I is a constant that will come out of as I square variance of xi. This is what it will become, right? Cool. Uh, okay. So okay, I mean this is a finite sum. Okay. So since okay, I mean maybe I'll write it down. Since variance of xi is given to you to be less than infinity, this means that variance of t, which is equal to 2 over n into n plus 1, I mean it will be something. So since it is IID, okay, maybe I will write it down. So 2 over n into n plus 1. Since they are IID, variance of xi for all I is the same, right? So maybe I can just take one of them, variance of let's say x1, the first one, and just take this I equal to 1 to n I square, right? And what will this thing become? Uh, Let me write it down. What is the summation of this I square? If you remember, I think it's n. What is it? Is it n into n plus 1 into 2n plus 1 by uh okay, I don't remember. Let me check it out. N, I square. It's a simple I write n into n plus 1 into 2n plus 1 by 6. Right, so I'll just write that down. 2 times variance of x1 n into n plus 1 into n into n plus 1 into 2n plus 1 by 6. This is what it is. Uh, Oh, by the way, I forgot. So this will be 2 square, right? Because these things are also constant. N square, 2 square, 2 plus n square. Okay. So this n plus 1 will cancel out. The variance of t, which this thing will become 2 into 2n plus 1 times variance of x1, right? So 2 will become 2 by 3. Okay. Just cancelling out, right? So this 2 will go and this 3 will. So this is what it is, 2 into 2n plus 1 by 3 into n plus 1, right? Into variance of x1. Now, since variance of xi is less than infinity, this thing is also less than infinity, okay? It's not going to infinity. Okay, so it's a constant. We can write it as some c, okay? Now you take your limits n tending to infinity, variance of t, that will become limit n tending to infinity to, let me, 2c by 3 into 2n plus 1 over n into n plus 1, right? So what will this thing become? The denominator is quadratic, whereas the numerator is linear, right? In n. So I mean, by the simple use of limits, you can see that this thing will become 0. Okay, this thing. So limit n tending to infinity, variance of t is equal to 0. This thing implies that the the estimator is also what? It is also consistent, right? So pretty straightforward. I mean, nothing very uh, like fancy, right? I mean, you just need to just keep your mind open. That's it. Let's look at the second question. I'm not sure how many questions we will be able to cover today. Okay, so I am just rushing a bit because I have some work. Nonetheless, I'm trying to like give you enough, solve enough problems to give you an idea, basic idea. Okay. Okay. So the next thing is as follows. So x1 till xn, these are all sampled IID from a uniform distribution, right? Uniform distribution with parameter 0, comma theta. Okay. And so you have T1, the first estimator. This is a moment estimator of theta. And you have T2, which is a maximum likelihood estimator of theta. Okay. So you are basically asked about this thing that uh, so T1 comma T2, like again, biased or not, consistent or not. Okay, this is the question. So we can start by first finding out what T1 and T2 are, right? What is the moment estimator and what is the maximum likelihood estimator of theta, basically. Okay. So for T1, so let's look at T1, right? Uh, so for T1, you look at the first moment only, right? So uh, basically, let's say x bar, which is equal to 1 by n summation I equal to 1 to n. So this is your first moment, right? This thing x bar is equal to what? What is the expected value of what is the mean of uniform distribution? Uh, the mean of the uniform distribution will be 0 to theta, right? 1 by theta times x dx, right? This is what it will be. This will become what? 1 by theta comes out x square by 2, 0 to theta. This becomes theta square by 2 and theta by, so this will be theta by 2, right? So the first moment x bar is equal to theta by 2. So this implies that theta is equal to 2x bar, or rather theta hat, right? Or basically this implies that T1 is basically 2x bar. So given n samples, your moment estimator tells you that use 2x bar as your estimate for theta. Okay, uh, cool. So what about the biasness and uh, consistency of this estimator? Let's look at it. So for biasness, you need to first find expected value of T1. What is the expected value of T1? So it's 2 times expected value of x bar, right? So which will be 2 times 1 by n summation I equal to 1 to n expected value of xi, right? What is that? 2 into 1 by n times. So these are all IID. Expected value of xi, as we saw just here, it's theta by 2, right? So I will write uh, n because n of them are being summed, n times theta by 2. So n gets cancelled, 2 gets cancelled. This is equal to theta. So this implies that expected value of T1 is equal to theta. That means it's unbiased, right? Because that is what we needed. What about consistency? Let's look at the variance of T1. Variance of T1, that will be 4 times variance of x bar, right? Using this thing. Now, what will be the variance of x bar? It will be 4 times 1 by n square, right? Into like summation of variance of xi, right? I equal to 1 to n. Okay. So now what is the variance of xi? Uh, does anyone remember that? Okay, I remember it. That is equal to 4 into 1 by n square times, if I'm not wrong, this should be n times theta square by 12. So it's b minus a square by 12. So theta minus 0 square by 12. So theta square by 12. And we are summing n of them. So that is why n. Okay, so n gets cancelled. 4 3s are 12. This becomes what? Theta square by 3n, right? Right. Now, if this is the case, then what will be the limit n tending to infinity variance of t1? This will be limit n tending to infinity theta square by 3n. So theta is a constant, 3 is a constant, n is going to infinity. So 1 by n as n goes to infinity is basically 0, right? So this implies that if this in the limiting case the variance is going to 0, that means that this is consistent. Okay. So T1 is unbiased and consistent, right? So I hope you can see that like all the calculations are pretty straightforward according to me. However, if you feel that something is not clear, just ping me, okay? Okay. Anyways, okay, moving on. Uh, okay, so this was just T1, right? So okay, this was T1. What about T2? How do you find? Let me just circle it so that it's clear what we are talking about. For T2, let us see, right? So what will be L of x, right? L of maybe I will write small x theta. That will be like this is the likelihood basically of the samples. That will be product of uh, okay. What should I do? Okay, maybe I will just write U uniform distribution of xi theta and I going from 1 to n, right? However, okay, yeah, this is what it is, right? So this is what, so it's like there you have n independent samples I going from 1 to n, and each of them has a uniform distribution. So the joint distribution, the likelihood basically will also be will simply be the product of uh, all of the PDFs basically, right? Now, what is this thing equal to? This thing is equal to product I equal to 1. So remember, your uniform distribution is looking something like this. So if this is 0, this is theta, and this is your constant, right? So this value is equal to 1 by theta, and afterwards, here and here, it's 0. This is important. So the value of the likelihood at a point is 1 by theta only if it is between 0 and theta, otherwise it is 0, right? So this thing will be equal to what? This will be equal to 1 over theta, right, into indicator xi, something like this. Xi is between 0 and theta, right? Because if it is outside theta, so let's say xi is here, then this thing will be 0, right? Otherwise, it will be 1 by theta. So you need to take care of this thing. Okay. So now, uh, right. Okay. So, what do you do? So now let's assume that one of the xi's is outside theta. Okay. It is outside theta. Then this whole product will go to 0, right? So, okay, what could be the maximum value of this product? This can either be 1 by theta raised to n if xi is it for all x for all I, right? So if for all I xi is between 0 and theta, this thing will be equal to 1, and hence 1 by theta will get multiplied n times, and hence the product will be 1 by theta raised to n. Otherwise, if any one of them is equal to 0, if any one of them is equal to 0, then this thing will become 0 otherwise, right? So the likelihood function looks something like this, right? So it is equal to 1 by theta raised to n if it's between this thing, or it's 0 otherwise, okay? Now, okay, so so the first thing that comes to our mind is that xi should be between 0 and theta. Only then we hope to maximize the likelihood. Otherwise, it is equal to 0, right? But remember what we have to do, right? We have to basically maximize this L with respect to theta, right? So theta MLE is equal to R max of L of x theta over theta. So you can also take log here and then maximize the log of this function. However, it doesn't matter. Like log is just for convenience, right? I mean, uh, you can either maximize this directly or you can take log and then maximize it. It won't matter a lot. Okay, so this thing is there. Now we can see that this can we hope to maximize this only if you know this is not the case, right? So this thing is equal to R max of theta. So this if this is not the case, then this thing is equal to 1 by theta raised to n, right? 1 by theta raised to n. However, there is a constraint now. What is the constraint? This thing. That 0 xi theta for all. So okay, I mean maybe I will draw a visual picture for you to just tell you, like, you can just arrive at the answer directly from it. So let's say this is your 0 and this is your theta, which is unknown by the way. Okay, you have to maximize uh, uh, okay, oh sorry. So so xi's are between 0 and theta, right? All xi's are between 0 and theta. So maybe x1 is here, x2 is here, x3 is here, maybe x4 is here, x5 is here, x6 is here, maybe x7 is here, right? So on. Maybe like x10 is here, something like that. So what should be the value of theta, right? So that this thing is maximized. So what I can do is, so let's say I call x sub n is like max of x size. Okay. So maybe x10 is your maximum, so xn will be equal to x10. So or whatever the maximum value that you observe. So you have n samples, you basically sort these values and see what is the highest value taken by these samples and call that x sub bracket in. Okay. Now, if since this thing is satisfied that xi is between 0 and theta, right? That will mean that xn is also less than equal to theta, right? Okay. What will this mean? This means that 1 over x sub n will be equal to 1 by theta, right? This is what you get. From here, what you can write? 1 by theta, just raise everything to power n. This thing will be less than equal to 1 by x sub n raised to power n, right? Now from here you can see, right, you have to maximize the value of this thing. And here you are getting an upper bound, right? That the maximum value that 1 by theta raised to n that it can take is this thing, 1 by xn raised to n. So this, so from here using this, what you can say is that theta MLE, which is the maximum value of this thing subject to this constraint, is nothing but 1 by x sub n raised to n. Oh, sorry. Uh, sorry. So you have to take R max, right? So this will be just your x sub n raised to n. sorry, not raised to n, which is equal to max of exercise. So I don't know if it was clear or not, but maybe I will repeat it. So theta MLE you can find by maximizing this L, this likelihood, and the value of this likelihood we just saw that has to be 1 by theta raised to n, otherwise it is 0, right? So it has to be 1 by theta raised to n. However, it comes with a constraint that all xi's should be between 0 and theta. Now, if all xi's are between 0 and theta, that means that the maximum of xi's, right, which we denote by x sub n, is is also less than theta, right? And using this inequality, we can say that 1 over x raised to x sub n is greater than equal to 1 by theta, and hence 1 by theta raised to n is less than equal to 1 by x sub n raised to n, right? And this is the maximum value that it can achieve, right? Because eventually we have to maximize this using this constraint, and this thing actually encapsulates both the things, that it is maximizing this objective function and it is satisfying this thing as well. So that is why theta, so the value of theta, when you take it to be the maximum of all xi's, your likelihood is maximized, and hence that is the MLE estimate. Okay. Uh, I don't know if it was very clear or not, but yeah, maybe we'll just leave it as a food for thought. Okay. So, so basically your T2 function, T2, that is basically max of x1 till xn, and we can denote this by x sub n. This thing. Okay. Okay. Uh, if that is the case, then what do you do? Now you have to basically find if it is biased or not, right? Simply. So just then, oh, okay, for that you need to first find the distribution of this thing, right? Uh, it's simple. So what is the so you always start with CDF, right? So what is the probability of x sub n less than equal to some x, small x, right? That, I hope you have done enough problems to know that this thing is equal to probability of x1 less than equal to small x times till probability x n less than equal to small, right? And all of them is basically, so you know the CDF of a uniform distribution. This thing, each of them is x by theta, right? It's a linear line, so it's a line from between 0 and theta, so x by theta raised to power n, right? So this is your CDF. So this is your CDF of xn, this random variable, and hence the PDF f of x. This thing will be what, d by dx, the differentiation of this thing, right? X by theta raised to n, and hence this is n x raised to n minus 1 over theta raised to n. Again, one thing to keep in mind is x should be between 0 and theta. That's all, right? So what is the expected value of T2 now? Expected value of T2, again, just a second. Yeah, sorry for that. So what will be the expected value of T2? Expected value of T2 will be nothing but you just integrate, right? 0 to theta x f of x dx. This thing will be equal to 0 to theta. What x? What is f of x? It is n x raised to n minus 1 by theta raised to n, right? Dx. So what will this thing become? Simple thing. 0 to theta n x raised to n. Theta raised to n will come out. Dx. This thing will become n over theta raised to n into x raised to n plus 1 over n plus 1. Uh, Going from 0 to theta, right? So this thing will become what? n over theta raised to n into theta raised to n plus 1 over n plus 1. This will become n theta over n plus 1, right? So you see this is not equal to theta, right? I mean, expected value of T2, where T2 is an estimator for theta, it's not exactly theta, it's a scaled version of theta. So this implies that this thing is actually biased, right? It's not unbiased, right? Simply because there is a scaling factor of n over n plus 1. Now, what will be the variance of T2? Variance of T2. This will be integral 0 to theta x square f of x, yeah, right, dx minus, this is expected value of x square, right? Expected value of x square minus you have to do expected value of x whole square, right? Now we just saw expected value of x whole square. This is n theta over n plus 1 whole square of this thing. Uh, what will this thing become? Uh, this thing will simply become what? Integral 0 to theta x square. F of x will be what? F of x will be, we just calculated it, right? So this is n into x raised to n minus 1 over n x raised to n minus 1 over theta raised to 1 dx minus n theta over n plus 1 whole square. This thing will become n over theta raised to n integral 0 to theta x raised to n plus 1 dx minus n theta over n plus 1 whole square. This will become what? N over theta raised to n x raised to n plus 2 theta raised to n plus 2 over n plus 2 minus n square over n plus 1 whole square into theta square. This thing theta raised to n, this goes out. This will become theta square into n over n plus 2 minus n square over n plus 1 whole square. This is correct. Yeah, I think this is correct. Right. So what will be the limiting case, right? So what will be the limit n tending to infinity variance of T2? This will be equal to limit n tending to infinity theta square n over n plus 2 minus n square over n plus 1 whole square, right? Now, theta square doesn't depend on n, so this will come out. The limit will go inside, and you can use the linearity because it's a finite thing. This will become theta square limit n going to infinity n over n plus 2 minus limit n going to infinity n square over n plus 1 whole square. So what will be this thing become? So the first thing here, this thing has the coefficient of n here is 1, here is 1. So eventually this, in the limiting case, this thing also will become 1, right? Minus here what this will, the here also the coefficient of highest power is 1, and here also the coefficient of higher power will be 1. So this will also become 1. This thing will become 1 minus 1, so this will become 0. So since the variance of this estimator is equal to 0, this means that this estimator is consistent, right? So what can we say about T2 now? So T2 we saw is actually, this thing is actually biased and consistent. So it's not unbiased, right? So it's biased. It is also consistent. However, it is consistent. So this is one of those examples where consistency is not enough, right? I mean, with if you have a large number of samples, you will keep getting consistent value. However, the value that you will get won't be correct because the estimator is biased. Okay. So yeah, well, I hope that this was clear, right? Uh, Maybe I will just solve one more problem, right? Because I have to leave early today. Uh, just a second. I don't something. Okay, cool. Okay, maybe I'll just solve one last question and then we can perhaps leave. Okay, so let's solve one more question. So today I am not solving a lot of problems, mainly because of the fact that I have some things to attend to. Uh, Okay, so I will just solve one more problem and then I'll finish. So here's the third problem. Okay, so again, this time we are given that x1 till xn, these are actually sampled IID from a log normal distribution. So f of x mu comma sigma, where f of x mu comma sigma, this is given by 1 by root over 2 pi x sigma e raised to minus 1 by 2 sigma square log x minus mu whole square, and x is greater than 0 here. Mu belongs to real numbers and sigma is greater than 0. Okay, this is given to us. The question that is asked is, what is the moment estimator for moment estimator for what? For mu and sigma square. These two, so we are asked to, basically find the moment estimator for these two things, mu and sigma square. Okay, so again, you have to do simple thing. First of all, you have to find what is the expected value of xi, right? Because, right, I mean, only then you can use, like, you need to find the first two moments for these two parameters. Only then you can proceed and use like solve equations to get the estimator for mu and sigma square, right? So the expected value of xi will be given by integral x f of x mu comma sigma square dx. Remember that integral will go from 0 to infinity because x is here greater than 0. Uh, Maybe I will leave it to you. Uh, Maybe I can try and solve. No, not an issue. This is 0 to infinity. You have x 1 by root 2 pi x sigma, right? E raised to minus 1 by 2 sigma square log x minus mu whole square dx. Right? This is given to you. So x gets cancelled, right? What will this thing become? What is this integral, right? Uh, do we know any trick? Well, it's actually simple, but okay, maybe I will just try and give you some. So use some change of variables basically. Okay, let's say p is equal to log x, right? Okay, so this means that x is equal to e raised to t. This implies that dx is equal to e raised to t dt. Okay, and use this change of variables and plug it in this integral. What will this become? So when x is 0, what will this thing become? P is log of x, right? So log of 0 will be minus infinity. And when x is actually infinity, log of infinity will be infinity, right? So the range of P is minus infinity to infinity. Okay. 1 by root 2 pi sigma e raised to minus 1 by 2 sigma square P minus mu whole square. Now e raised to P dp, right? So if you look at it, uh, this is like a Gaussian distribution, right? This is a PDF of Gaussian distribution, right? So this is actually expected value of e raised to P, where P is actually sampled from normal mu comma sigma square, right? And we know what this thing is actually because this is nothing but your this is your moment, sorry, this is your characteristic function, right? This is your characteristic function. So I don't know how to. So yeah, phi of s was given to be expected value of e raised to s st s maybe sp. Okay, and this is just what this is actually equal to phi of one, right? Phi of one because s is 1 here, right? This gives it. And we know what is the moment generate so characteristic function of your normal random variable, right? So this thing will become what? E raised to, if you remember, it is mu plus uh, s sigma square by 2. S is 1, so this will just be sigma square by 2, right? So yeah, so this is the your like first first moment. X bar is equal to e raised to mu plus sigma square by 2. Similarly, using similar thing, what you can do is you can now calculate variance of xi, and you can actually use again the same thing. Okay, uh, it's not difficult. I will just write down the final expression. This is e raised to sigma square minus 1 e raised to 2 mu plus sigma square. This is what it is, right? And so this is equal to your s square, basically, your variance, right? Okay. So now you have your two variables, right? So x bar is equal to e raised to mu plus sigma square by 2 and s square is equal to e raised to sigma square minus 1 into e raised to 2 mu plus sigma square. So this is your 1, this is your 2. You need to basically solve for mu and sigma in terms of x bar and s bar, right? Okay, so how do you do it? Simple, just use use what you know. Simple as that. So take log here. Log of x bar will be equal to mu plus sigma square by 2. Uh, this means that you just multiply by 2 on both sides. It will become 2 mu plus sigma square. This will be 2 log x bar, right? Substitute this thing here, right? What will this thing become? S square. Okay. What is s square? S square is equal to e raised to sigma square minus 1. And this thing, 2 mu plus sigma square is 2 log x. So 2 log x bar, right? Now what you will do? What should you do? So now you can do is the following. Uh, take log on both the sides, right? So this will become 2 log s equal to 2 e raised to sigma square minus 1. This so log of this thing plus log of e raised to 2 ln x. So this is 2 ln x bar, as simple as that. We bring this thing here. This will become 2 ln s by x bar because it will be minus. It will become log of e raised to sigma square minus 1, right? So now what? This thing means that e raised to sigma square minus 1 is equal to s by x bar whole square, right? Just take 2 again inside the log. This is what it will become. and hence you get e raised to sigma square is equal to s by x bar whole square plus 1, right? And hence sigma square is equal to log of s by x bar whole square plus 1. This is what you get, right? This is your sigma square. Now use it to basically find mu. Use this thing again, right? So we have 2 mu plus sigma square is equal to what? Uh, 2 log x bar. 2 log x bar. Yeah, maybe call it 3. Use 3 and substitute it here, right? So what will this thing become? So maybe, okay, I can just write from here, right? Mu is equal to 2 ln x bar minus sigma square by 2, which is equal to log of x bar minus sigma square by 2. Okay. Uh, you know the value of sigma square here. Just substitute it. So mu will become log of x bar minus 1 by 2 times sigma square, which is log of s by x bar ka whole square plus 1. Okay. Can we simplify it further or is it done? Hmm, maybe you can do some simplification. Ln x bar minus half log this do this thing s square plus x bar whole square, right? By x bar whole square. This is what it will become. This will become log of x bar minus 1 by 2 times log of s square plus x bar square minus log of x bar square, right? This thing is in bracket. Uh, so I think this thing will become um, ln of x bar minus half log of s square plus x bar square minus minus will become plus 2 x the square will come out plus 2 ln x bar by 2. 2 2 gets cancelled. This thing gets added to this thing. This will become 2 ln x bar minus half ln s square plus x square. This is your value of mu. And your sigma square was what? Sigma square was this thing. Log of s square by x bar square plus 1. So these are your basically estimates, right? I mean, these are your basically moment estimates for mu and sigma, right? Nothing, just a lot of simplification. So in estimators, you just have to do a lot of uh, simplifications. That's all. So yeah, I think this was the last problem that I was going to solve today. I know the session was a bit small today because I designed it that way. Uh, yeah. However, I mean, if you have any problem, you can just ping me in the chat or mail me or do anything to reach out to me, and I will answer your queries there, right? Yeah. However, today I have to attend to some business and I have to sort of leave early, so that's all for today. Uh, yeah. Thank you for listening and yeah, have a great day. Okay. Uh, thank you. Goodbye.